Alrighty, y'all. Today we're going to be taking a look at our E field as caused by a charge concentration. Right? And we did a bit of this in lecture, and we did a little bit more in recitation. But today I'm going to be going into a little bit more of a deep dive of how we get the equation that we were looking at from an integral, and really just the basic concepts of what all of it means. Right? So first thing I'm going to talk about, right, we need to get the E field as caused by a charge concentration. Well, first we need to understand what our E field or electric field really is. All right, we know that our positive point charge here and our negative point charge, we have our field lines coming out of our positive point charge and going into our negative point charge. Okay? But why, really, is the question we're trying to ask. So we're going to work through and figure that out real quick before we get started on the harder part, which is the charge concentration. Okay, so I'm going to start with something that we should all be a little bit more familiar with, which is an electric force between two particles, two charged particles, right? So I have 1 and 2, right? So we know that my force of 1 on 2 is going to equal Coulomb's law, KQ1, Q2 over R squared, right? And a force is a vector, so I'm going to put that little vector symbol, and R hat is just going to say in this direction, right? I put a hat on it, my R hat, that's saying it's a unit vector, and in this case, R hat is pointing in this direction. Okay? And from Newton's law, we also get that our force of 2 on 1 is going to be equal in magnitude, but opposite direction. Right? So now, I'm going to jump over to E field because we're going to say, what if our Q2, what if that wasn't there? What if it was just a point in space that we cared about, that we wanted to get some information about, but there wasn't actually a second charge? Right? So we saw at one point in lecture we had that equation, right? Our E field equals our force divided by charge. Well, so let's look at our situation between here and here. We have our force between, our E field, right? And this is our E field as caused by point 1 at point 2. As caused by charge 1 at point 2, right, because there's no charge at point 2, that's going to equal our force, right, our force between 1 and 2, from 1 acting on 2, divided by Q2, right, because Q2 doesn't exist anymore, so we're going to divide it out of our equation because we don't care about it anymore. Okay, so if I pull my Coulomb's law down here, right, and I divide out by Q2, right? It's going to cancel. That's going to leave me with KQ1 over R squared, R hat, right? And remember that our E field is a vector, so it's going to also have this R hat unit vector giving us a direction, because we have our magnitude and our direction. And it makes sense that it's the same R hat because my force of 1 on 2 is going in the same direction as my E field of caused by charge 1 acting on point 2, right? And this also makes sense, right? Because really what our E field is talking about, what our E field is saying is, hypothetically, what would happen if I put a 1 Coulomb charge at this point, right? Because in reality, right, we have our charge 1, and we want our E field at this point here, right? I went from a situation with a charge to none, but if we're just looking here, there was never a charge here, there never will be a charge here, but I want to find the E field at this point. All right, we'll call this just point 2 again. So in this case, what I'm going to say is what my E field really is, it's a hypothetical force, right? So let's pretend that we have a charge here, right? We're pretending that we have a 1 Coulomb charge here. So I'm going to have my Coulomb's law, F of 1 on 2 equals my K, Q1, Q2 over R squared, R hat, right? But we said that this was a 1 Coulomb charge. So we have K, Q1 times 1 over R squared, R hat, right? Which becomes K, Q1 over R squared and the R hat, right? Because we're just multiplying by 1. It's not going to change our value at all. It's not going to change our direction. So that's going to be my force of 1 on this hypothetical 1 Coulomb charge. That looks like an H, but it's plus 1, right? This is really what my E field is, caused by 1 acting on 2. It's the hypothetical what I would say, like, if there was a charge here, this is the force that would be acting on it. But there's not a charge there, so we just get to report an E field. And that makes sense too with our newtons per coulomb, right? Because that's saying how much force, right, newtons, how much force would there be for every 1 coulomb present? Right? We said there was 1 positive coulomb, right? How many newtons for every 1 coulomb? Okay? And that comes back up here. That makes sense for this too. We said it was a positive, pretend 1 coulomb charge. So our force, as caused by this one on this one, is always going to be repelling, right? My positive charge is going to repel this hypothetical positive charge. So the force is always going to be going away from my positive charge here. But if I go to my negative charge, again, my test charge, 1 coulomb, 1 positive coulomb, it's going to want to attract that 1 coulomb. So the force is always going to be going towards my negative charge here. Okay? So that was just a brief recap on our E field, what our electric field is. And now let's get into the fun part of actually working through how to get the E field as caused by this charge concentration, this charge distribution over a rod, over an arc. All right, like I did before, I'm going to start with something we do know how to do, right? I'm going to say every single one of these is a point charge, right? If I had a bunch of point charges, all I would have to do is find the E field as caused by each of them on this point. E field is caused by each of them, and add up all of those vectors, right? And I have this larger circle here just to show that this point P is at the center of this arc if it would be a larger circle, but I'm going to get rid of that and give myself a little more space to write here. All right, so we're going to pretend that it's a bunch of point charges, and I just have to add up each of their E fields, right? So this one would be causing an E field going like this way, this one would be like that way, et cetera, and so on and so forth. I'm not going to draw all of them, but that's the gist of what we're looking at, right? We don't know how to get the full thing, so we're going to break it up into pieces that we do understand how to work with, right? So I'm going to do my E field equals, right, our KQ over R squared in the R hat, over R hat, right, because this is for our singular point charge. But what I want to do is I want to add all of them up. So what I'm going to do, really what I'm going to want to do is I'm going to take the integral of this whole mess. So I'm going to have to take the integral with respect to something, but we'll get to that part in a second, right? I want to take the integral, because what an integral does is it adds up all the pieces. Right? We've seen integrals before. If we haven't, that's fine too. Right? But we've seen them to find the area under a curve, right? If I wanted to find the area under a curve, if I were just to approximate it, I would draw a bunch of rectangles, right? I would say, here's my first rectangle. Right? I get the area of this rectangle doing my base times some height, right? And then that's my area of that rectangle. And then I get a bunch of these rectangles, get the area of each one, and then I add them all together, right? So area of this one plus area of this one plus this one plus this one, all the way, all the way down, right? The way I would make this more accurate, right? Obviously there's going to be, I drew it up here, some margin of error where my rectangle, my curve, is not going to line up perfectly with this rectangle. So I'm going to have a little bit of error. The way that I get the smallest amount of error, I get the most accurate answer, is if I took a super duper thin rectangle, right? I get an infinite number of these super tiny rectangles, and I add up all of their areas and say, that's going to be the area under my curve, right? So what I say is I have this dx, right? And the height of my rectangle, right? This dx is an infinitely small little chunk of x. and I have my height of my rectangle, well, that's just going to be the value of the function at this value of x, right? So that's really all I'm saying. When I take my integral of f of x dx, that's just saying add up a bunch of rectangles that are base times height, this area, add up all of these areas, and you can bound it, say 0 to a, right? That means my x is going to go from 0 to a, and this gets me my area under this curve. We're going to do the same thing up here, right? We want to get infinitely small point charges along this curve, and we want an infinite number of them. That's what our integral does. We're summing up an infinite number of infinitely small pieces, right? So if I were to do that, I said I wanted an infinitely small point charge, right? Well, our radius, our distance, isn't going to change. I'm going to call that big R, right? That's going to be the same for every point charge along here, right? But Q, right, that's going to be some tiny piece. I'm going to say, right, this is going to be my integral, and I'll put bounds on it in a second. I have K over R squared, dq, right? R hat, right? Well, I can put dq at the end because that's really how we're used to seeing it. We do some function integrated with that, right? dq, right? For every single tiny point charge, right? Every tiny x that I wanted, every tiny rectangle, I wanted the area of that. Every tiny piece of charge, I want the field as caused by that, and I want to sum them all up, right? So now we have our infinitely small pieces. Now what we're going to say is that our dq, well, I don't know how to integrate this right now because I don't have all this as a function of this. So I'm going to say that we're going to bring in this lambda, right? This is our charge per unit length, right? And then multiply that by dl, right? So I have charge per unit length, and I'm multiplying by a length. So all this is saying is how much charge per unit length, right? And instead of saying I want a tiny one of these point charges, I'm just going to say, like I did before when I had my dx, I wanted an infinitely thin rectangle. I want an infinitely tiny chunk of this, an infinitely tiny length of my larger curve, right? So my dl is going to go from here to here, the same way that my x went from 0 to a. And my L, my length, is going to be a bunch of tiny charge pieces going along here. And I multiply by lambda because charge per length, multiply by length, that's just going to leave us with our charge, right? So that's what we're trying to get to. Remember, we have to keep our equation the same. We can't just be throwing things in, right? We want this to be our charge so that we stick to our equation for our E field. All right, well, the next thing is to figure out how do we figure out dl, right? So this is dl. Well, really what dl is our arc length, right? If I were to say this whole thing is L and this little bit is just a tiny piece of it, right? Our arc length is our total thing. So if I get my S for arc length, really it's going to be our ds, right? Because we're taking a tiny piece of it. My equation for arc length is r times theta, right? And this equation comes from our equation for the circumference of a circle. So if I go up to this corner here and I have my unit circle, right? We know that the full circumference of a circle equals 2 pi times r, right? That's just saying take my radius and go 2 pi radians all the way around my circle, right? So that's my r times theta. It gives us that arc length. Really, if we're saying, like, I want to go a quarter of the way around the circle, so I want the length of that, I'm going to say that's going to be 1/4 of my total circumference, right? Dividing by 4, that's going to be pi over 2 times r. So we have r, so my theta for going a quarter of the circle is pi over 2, which we know it is, right? Quarter of the circle, Right? That's where our theta, our equation for our theta comes from, right? So now I have, right, lambda times r d theta. Again, because I said before, r is going to be the same for all of these. The thing that I change to get from this dl to this one to this one to this one to this one, it's going to be the theta that I'm going around my curve with, right? So theta is going to be an angle with reference to something. Let's say if 0 theta starts like here, then here would be a certain theta. And again, I want this to be an infinitely small angle so that I get an infinitely small arc length so that I can have an infinitely small piece of charge, right? We always want to make sure that we remember why we're doing the random things that we're doing. They all serve a point, I promise, right? So now we have dq, and that's in terms of lambda and r and d theta. So we can plug that in up here. So I have my integral k over r squared times lambda r d theta. All right, and we can see r in the numerator and the denominator. So it'll leave us with integral of k lambda over r d theta. Okay, we've simplified it. Now let's make it a little more complicated, because I just introduced this lambda for my charge per unit length, but I was given the charge of the whole thing. So I know I want charge per unit length, so I'm going to take my charge and divide by the length, right? So that gives me my big Q over, and again, we're going to say our arc length is r times theta. In this case, this is the theta that's going all the way around, so from here to here. So it's going to be 2 times alpha. And I'm just using alpha as a placeholder for any given variable. So 2 alpha times r. That's going to be our lambda, right? Because this is our arc length. Charge divided by length gives us charge per unit length. Right? So I'm going to take this, plonk it in over here, and that's going to give us our integral of kq, right? Because q is in the numerator. I'm going to just bring this down to the denominator for us, over 2 alpha. I have an r from the denominator over here. I have an r over here. It's going to be r squared d theta. Oop, I have been missing a part this whole time, right? I completely skipped over writing that r hat. Remember, because our E field isn't just a magnitude, it's also a direction, right? Because it's a vector. I'm going to put this in to each one here, right? Because we want to keep track of that r hat, right? Because what would happen is if I just summed up my magnitude, I said integral kq over 2 alpha r squared d theta, right? This is just summing up, and again, integral, summing up my magnitudes of each of the E fields, right? But my E field as caused by a point up here, right? This is a positive charge, so it would have it, right? We said it would be going kind of like this way, and then over here would be going like this way, right? If I were to just add these magnitudes together, I would get something that looks like twice as long as this, right? So it would be this length plus this length, right? So I'd end up getting a vector that's twice as long, but really, I can't just add the magnitudes of vectors. What I have to do is I have to add my x and y components. And in this case, my y components like there, my y components there, they're going in opposite directions, and they're gonna cancel out to some extent. Right? We can't just add up all of our magnitudes. We have to also consider this r hat. Right? So this is bad. We also have to consider this r hat because that gives us our vectors, right? Well, we're integrating with respect to theta, so we have to get r hat as a function of theta so we can integrate. So right now, k, q, 2 alpha, r squared, none of those depend on theta. Right? It's a pretty boring integral right now because these are all constant. If I'm changing theta, right, these are all just constants that I could just pull out. Right? So I'm going to need to get r hat as a function of theta. So I need to have r hat as some function of theta. All right, and now we get the fun part of figuring this out. And we revisit our unit circle. We remember that like x and y directions come from trig, and we can go around using sine, our x and y as functions of sine and cosine of theta. Right? That's how we get some coordinates on this. So we're going to use the same kind of idea over here. So I know that I'm going to say theta equals 0 is, I'm marking pink. This is going to be my theta equals 0. Right? Those look very similar, but I promise one is a theta and one is a 0, right? So I need theta to go from negative alpha to positive alpha. And first of all, those are going to be the bounds of our integral, right? Negative alpha to alpha, right? So now I just need right, I have my magnitude all set, and it's going to go from negative alpha to alpha. Now I just need my r hat as a function of theta. So if theta is 0 here, right, I know my E field is going to be pointing like this, right? Because this is the point that I'm looking at here. It's going to have an E field that causes it to go this way, right? So I'm going to just see that this is negative in the x direction and 0 in the y, right? That makes sense, right? So what this is going to tell me is if I want this to be a unit vector, it has to be 1 in the x and 0 in the y, right? That gives it a magnitude of 1. And the way we figure out our sine and cosine functions is I want when theta equals 0, right? So that gives us, if I go back over here, r hat of 0 has to equal negative 1 in the x, 0 in the y, right? Which is going to essentially just equal negative I hat, right, if we write that in vector notation. Right, so what sine and cosine gives us this? Well, when theta is 0 up on our unit circle, oh my god, there we go. When theta is 0 here, right, we have cosine equals 1 and sine equals 0. So that's what we're going to start with. We want that it's going to be cosine of theta in the I direction, right? Because we want it to be a magnitude of 1 when theta is 0. And we want sine of theta in the j hat direction, because when theta is 0, sine is 0, j or y is 0. Right? But we said we want it to be negative 1, so I'm just going to say negative cosine. Okay? And as our theta is increasing here, as theta increases, we want y to be positive. As theta increases, we actually want y to be negative. That's my bad, right? Theta increases in this way, so if I have a max theta up here, our y of this is actually going to become negative. So I'm going to have it also be a negative here, right? Because in our real unit circle, if theta is increasing along here, our y is going to be positive, but we just want to flip that direction for us. So this is going to be our equation for r hat as a function of theta. Right? This is probably the trickiest part. Right? We just have to remember that we're really trying to break our vector into x and y components. Right? It's going to be negative cosine in the x direction and negative sine in the y. Right? So if I really had, say if I was, I'm going to pull another color. Let's do blue for this one, right? Let's say I was here, right? I have some theta equals, let's call it pi over 3, right? Just some random theta, right? If I were to follow this line, here is my E field vector, right? I have theta equals pi over 3. That's that angle in there, which means it's also that angle, right? Because they're the same. So I want my y and x components. So if I were to do the trig for this, right, I would have my E field vector times, I have this, I want sine is going to be y, so E sine theta equals my y direction, and E cosine theta equals my x direction. right? So here's what I said. I said sine and cosine. It's really what I'm doing. I'm taking that r hat and I'm multiplying it by the magnitude, right? So sine and cosine, but that's going in the negative y, that's going in the negative x. I get to do that. That's all I'm doing with this. That's just breaking it into components for me continuously, right? So now I plug this all in, right? And again, I have unit vectors, I and j hat, because that's going to give my thing, my vector direction as well as magnitude. I'm going to take this, plug it in for my r hat, put in parentheses. Ooh, I'm still writing in blue. Put in parentheses, and again, we're integrating d theta. All right, and like I said before, I can pull all of this out because none of this changes with theta. So I pull all of that out of my integral, right, because that's just my magnitude at each point. 2 alpha r squared, integral from negative alpha to alpha. All right, so I'm just integrating. I'm actually pull out the negative too, just for ease right now, because it's going to be cosine theta I hat plus sine theta j hat d theta. Now we're getting super close, because now all we have to do is evaluate our integral. I'm just going to move over here so I have a little more space to work. All right, we're just evaluating the integral. So my integral of cosine, that's going to be sine of theta, and that's times I hat, right? So I hat and j hat are like constant vectors. They don't move, they don't change. So our I hat and j hat, we're going to treat them the same way we would treat a constant if it was just like 2 times cosine of theta, right? We just keep that constant there. We just multiply our final answer by that. All right, so I have my magnitude on the outside, almost forgot. 2 alpha r squared all times sine theta I hat, and then our integral of sine is going to be negative cosine theta j hat. All right, and that's evaluated from negative alpha to alpha. All right, we're almost there. We're getting so close. All right, so now if I plug in negative alpha and alpha, I'm again just going to keep this on the outside so I don't have to write it out the whole time. So I plug in alpha, I have sine of alpha I hat minus cosine alpha j hat minus sine of negative alpha I hat, and then minus a negative, right, because you do upper bounds minus your lower bounds, so I'm just going to flip that sign, plus cosine of negative alpha j hat. Okay, now let's see how we combine these here trig functions. All right, so we have sine of alpha and sine of negative alpha. All right, so what I'm going to do, I'm going to come up and look at my unit circle. If I have the sine of some number, right, some angle here, right, my sine of that is going to be this y component. If I go in the opposite direction, I go in negative, so here's my alpha, here's my negative alpha, right? Instead of going up that amount, it's going to go down that same amount. This gives us an identity that we might be familiar with, where sine of some angle is going to equal negative sine of the negative angle, right? Or in other words, if I do negative sine of alpha, that equals the sine of negative alpha, right? Which helps us, right? Because we have a negative alpha in here. So if I rewrite this as this is going to be a negative sine alpha minus a negative sine alpha, that's going to be sine alpha from over here, I hat, plus sine alpha I hat from over here. Cool. Now let's take a look at these cosines. So I'm going to look at something similar. If I go, getting rid of all this mess, it's all in my way. If I go up a certain angle, it's going to go, I'm going to get a different color to see this, right? It's going to go some distance in the x direction. Well, I just kind of drew it, but if I have go that positive angle, it's going to have some value in the x. If I go a negative of that same angle, right, it's still going to the right in x. It's still going to have the same cosine. right? It's another identity where we have cosine of some angle is equal to the cosine of the negative angle, right? They're the same thing. So what that means for us down over here, almost got lost for a second, is that this is just going to equal cosine of alpha. So then what that gives us, we have a positive cosine alpha here and a negative cosine alpha here. That's plus cosine alpha minus cosine alpha, both j hat, right? Plus a thing minus a thing, those are going to cancel. That's going to leave me with negative kq over 2 alpha r squared, right? Because remember that's still our magnitude up here, times 2 times sine alpha I hat, right? Because 1, 2 multiplied by 2. Right? 2's are just going to cancel real quick. Right? Negative kq over alpha r squared times sine of alpha in the I hat. Right? And we have a negative magnitude going in the I hat direction, which makes sense because if we look at all the things that cancel, I just get rid of all this mess, right? I drew it before that our y directions are going to cancel for this. This makes sense for what we talked about in class because if we draw our axis of symmetry, right, along here, that's our net E field is going to be along that line. Right? And we just figured out that it was in the negative I hat direction, and that's exactly what we expected because it's going to be going along this line of symmetry in the positive, and this is a positive Q, so it's going away from our positive charge like we said up here. All right, that's a lot of math, and that's a lot of calculus. I hope that made a little bit of sense. We're going to go on to another quicker example problem just to take a look at, right? Now we're going to think about what would happen if our Q was negative. So I'm going to go up here. I'm just going to steal some of my work from up here. And we're going to rethink what has to change. If it's the exact same problem, we're going from negative alpha to alpha, right? All of this, it's the exact same problem, but instead of a positive Q, we have a negative Q. All that's going to change for us, right, because I said up here we were looking at, right, when theta equals 0, our r hat was over here. Well, this time when theta equals 0, we have r hat going this way. So that's the wrong r hat. This time, r hat's going towards our negative charge, right? Again, we can see our line of symmetry. We expect it to be going along that line, right? And as theta increases, we want a positive y. So the only thing I'm going to do is get rid of this negative sign for my r hat. And all the math is going to be exactly the same, right? Remember, I factored out that negative pretty early on, so it would make my math easier. All of this math is going to be exactly the same. The only difference is that negative sign in front of my magnitude there. All right? And that's what we expect, right? Now we have a positive in the I hat direction, and that's what we said we expected along that line of symmetry. And since it's negative this time, going towards that curve. Right? Well, now what happens, right? We saw that our j hats canceled out for us here, but now what happens when we're not aligned over that x-axis, right? We're going back to a positive q on here, but what happens when we're not along the x-axis? Now we're along the y-axis. Again, it's going to be mostly the same. I'm going to steal this. We just have to change what we're thinking of as our r hat, right? So in this case, I'm going to say my theta equals 0 is still along this line of symmetry, right? Again, we have a positive charge now, so that means my E field lines are going to be looking like this. All right, my E field mini vectors that I'm adding up are going to look like that because we're going away from our positive charge. This time, when theta equals 0, right, and again, I'm going negative alpha to alpha, right, same bounds. This time, when theta equals 0, my, I want it to be, x has to be 0, and y has to be -1. And then as theta is positive, my x is going to be going positive. Oh, yes, my x is going to be going positive as well, right? So as theta is going this way, right, here's my x and y components of this field vector down here, right? So same thing that I did before. I have to use sine and cosine. I want x to be 0 at the beginning. That means that instead of this, I'm going to have sine of theta, and my cosine is going to be over here, right? And again, I want it to be a -1 for y to start off with. So that means I'm going to have a negative over here. And then as theta gets more positive, I want x to also be positive. So I'm going to leave that just like that. All right, and now this time when I integrate, pull this part out again, and then this is going to integrate to be, oh god, testing my integration skills, negative cosine theta. I'm just trying to do it fast, that's why it's not a bad integral to do. I'm just trying to rush through for the sake of the video. Minus sine theta j hat, right, evaluated from -alpha to alpha. And again, we can start plugging things in. We're going to say that negative cosine alpha I hat minus, actually I'm going to pull that negative out as well. So it's going to be negative kq over 2 alpha r squared. We're just going to make everything positive, right? 2 alpha plus sine alpha j hat minus cosine of negative alpha I hat minus sine of negative alpha j hat, right? I'm getting kind of messy, but you get the point. All right, same kind of identities. All right, what's going to cancel for me is, remember, our cosine of a negative alpha is the same as cosine of alpha. So cosine alpha minus cosine alpha, those are going to cancel. And then sine of negative alpha actually equals negative sine of alpha. So it's going to be negative sine of alpha. So that's also going to be negative kq over 2 alpha r squared times 2 sine alpha j hat. All right, and again, our 2's cancel out. And we can see that it leaves us with the same magnitude that we had before, alpha r squared sine alpha j hat, right? It's the same exact magnitude, right? kq alpha r squared sine alpha. But this time we're going in the negative j hat direction. It's the only difference. It all works out the same. Well, now what happens if we're not centered over an axis at all? Right? Before we were saying, oh, all of our x components are going to cancel, and oh, all of our y components are going to cancel. Now what? Right? So again, I'm going to steal this equation, and we're just going to change. Remember, these sines and cosines with our I hats and j hats, those are really just, this just represents our r hat vector, right? So now, again, I'm going to do the exact same thing that I have been doing. I'm going to find my theta equals 0. This time I'm going to say here is theta equals 0, just so it matches up with my unit circle, right? And that's just easier for me to think of. So this time, instead of going from negative alpha to alpha, I'm going to be going from 0 to 2 alpha, right? And when my theta equals 0, right, it also makes it easier to figure out. If I set my 0 here, it makes it easier to figure out what my sine and cosines are supposed to be, because if I set my 0 theta here, then I wouldn't be able to do my fun trick where I say, oh, one of them is 0 and one of them is not, or x is 0 and y is not 0. So that gives me my sine and cosines. If I set 0 here, then x is -1 and y is 0, right? Same trick I've been using. So that to me says that x is going to be cosine, negative cosine theta, and y is going to be sine theta. And when theta is getting bigger, my y, or when theta is going positive, my y is going to be going negative, which means that it's going to be negative like that, right? Which is a familiar thing, right? This is exactly the way we set up for this one, right? or not this one, sorry, this one, right? We had our negative and our negative that we just pulled out to the front, and it all worked out. But in this one, we were integrating negative alpha to alpha. This one, we're integrating from 0 to 2 alpha. So again, I'm going to pull that negative out. So I'm going to go, it's going to be negative KQ. I am not doing all of this in purple. I just changed my mind on that. So that's going to give me a negative KQ over 2 alpha R squared. Right? And my my integral, right, it's going to be a positive cosine is a sine theta, that's an I hat. And a positive sign is a negative cosine theta j hat. Right? And all that's evaluated between 0 and 2 alpha. All right, so this time we have negative KQ over 2 alpha R squared. We plug in our 2 alpha, sine of 2 alpha, I hat, minus cosine of 2 alpha, j hat, plus, minus actually, sorry, sine of 0, I hat, plus cosine of 0, that's a theta, cosine of 0, j hat. All right. This is a whole mess, right? So now let's start simplifying this. All right, sine of 0 is just 0. All right, and I have, all right, cosine of 0, that's going to be 1, so that's just going to be a j hat. So I have negative KQ over 2 alpha R squared, and I'm going to sort it by I hat and j hat, so it's going to have I hat times sine of 2 alpha minus, we'll do plus j hat times cosine of 0 is 1. All right, I'm just doing this minus cosine of 2 alpha. All right, 1 minus cosine of 2 alpha, really, that's what that's saying is, because cosine goes from 0 to 1. Oh, come on. Goes from 0 to 1. So saying 1 minus cosine of alpha is really saying cosine, or 1 minus cosine of 2 alpha is really saying cosine of 90 minus 2 alpha. All right, because if I have my, I'm going to do a different color, all right? I'm going here, right? Here's my cosine of it. If I did 1 minus it, that's going to give me this chunk here, which is really saying the cosine of if I did 90 minus this alpha, which is, right, so here's my 90. If I subtract that angle, right, is that right? Let's ignore that for right now. Am I right? I might be right. 1 minus cosine alpha is cosine of 90 minus alpha. Yeah, because then if I was doing the cosine of this whole angle, then I would have to put it on a new unit circle, but it's a much larger angle, so now it's going to about here-ish, say, and there's my purple line. Sorry, I was right. This is just trig identities type thing that we have to remember. All right, so we have negative KQ over 2 alpha R squared, all right, and then sine 2 alpha in the I hat and cosine of 90 minus 2 alpha in the j hat. All right, again, here's like our magnitude, and this is essentially giving us our direction, because we know that here's our line of symmetry. We're going to be going along here. So if this is if I'm looking along this line, we're looking like this. Here's my alpha. Here's going to be my x and y components, right? We can see that x and y are going to be negative, right? That gives us this. Right? And we're dividing everything by 2. That's the reason that it works out, because, right, we can do our trig out. It normally would be saying like seeing sine and cosine, but it's flipped, and also we're dividing it out. Either way, my math is a little wonky on this part. We're just gonna kind of ignore all of this. My bad for picking a problem that it's really hard to do with unit circle identities that I don't remember off the top of my head. The point that I was trying to make was that, right, in all of these, either our x direction fully cancels out or our y direction fully cancels out. But that's not always the case, because sometimes we can be left with both x and y components when we're in a weird, tricky situation like this. Okay. Well, I hope you found this video. I know it was a bit of a long one, but I hope you found this at least a little bit helpful. Let me know if you have any more questions about this or anything else that you want me to try to explain, and I'll do my best to try to explain it, because I guess Sydney explains stuff.